In our universe, everything is supposed to follow rules. But somewhere in space, a black hole exists that should not exist at all. And its discovery is forcing scientists to rethink the laws of physics. For most of the 20th century, black holes were little more than strange mathematical ideas. They appeared in Einstein's equations as extreme solutions, places where gravity becomes so powerful that space and time collapse inward. Even Albert Einstein himself believed nature would never allow such objects to form. To him, black holes felt like a flaw in the mathematics, not a feature of the universe. For decades, they remained theoretical. No light escaped them. No image revealed their shape. There was no direct proof they existed. And yet, slowly, evidence began to accumulate. Astronomers observed stars moving at incredible speeds around invisible objects. They detected intense X-ray emissions coming from empty regions of space. And eventually, they measured ripples in space-time itself, gravitational waves produced by massive collisions far beyond our galaxy. By the early 21st century, black holes were no longer hypothetical. They were real, measurable, and surprisingly common. But as scientists began to study them in greater detail, something unsettling emerged. The universe was not behaving the way our theories predicted. According to modern astrophysics, most black holes form at the end of a star's life. A star exists in a delicate balance between two forces, gravity pulling inward and nuclear fusion pushing outward. For millions or even billions of years, these forces cancel each other out. But when the fuel at the star's core runs out, the outward pressure disappears. Gravity wins. The result is collapse. If the star is massive enough, this collapse triggers a supernova explosion, one of the most violent events in the universe. What remains after the explosion depends entirely on mass. Smaller remnants become white dwarfs. Heavier ones collapse into neutron stars, objects so dense that a single teaspoon of their material would weigh billions of tons. And only the most massive stellar cores collapse further, forming black holes. But physics predicts limits. There are strict boundaries that determine what is possible and what is not. One of the most important of these boundaries is known as the black hole mass gap. According to theory, stars within a certain mass range should never form black holes. Instead, they should destroy themselves completely through a process called pair instability, leaving nothing behind. No remnant, no black hole. For decades, this prediction held firm. The mass gap was considered one of the most reliable results in stellar physics. Observations matched theory. Models worked. The universe appeared consistent. Until it didn't. In 2019, astronomers studying a star system in our own Milky Way galaxy made a discovery that immediately raised alarms. The system, known as LB1, appeared unremarkable at first. A massive blue star was orbiting something invisible. Binary systems like this are common, but when scientists measured the motion of the visible star, they noticed something was wrong. The star was moving too fast. The only explanation was gravity, extreme gravity. The invisible companion had to be incredibly massive. When researchers calculated the mass of the unseen object, the result was shocking. It appeared to be a black hole with a mass far larger than expected, sitting dangerously close or even inside the forbidden mass gap. According to established theory, such a black hole should not exist. The reaction from the scientific community was immediate and cautious. Extraordinary claims demand extraordinary evidence. Some researchers argued that the measurements must be wrong. Others suggested the system might contain multiple stars instead of a black hole. Distance estimates were questioned, models were re-examined, assumptions were challenged. But even as the original estimates were revised and debated, the core mystery remained. The object was still too massive to fit comfortably within existing models. The mass gap, once thought empty, was no longer empty at all. And this discovery was not alone. At the same time, gravitational observatories like LIGO and Virgo were detecting black hole mergers across the universe. These detections revealed black holes colliding with masses far larger than expected. Some black holes appeared to have formed incredibly early in cosmic history, when the universe was too young to have produced them through standard stellar evolution. Again and again, the data pointed to the same conclusion. Our understanding of how black holes form was incomplete. Scientists began exploring new explanations. One possibility is that some black holes are not first-generation objects. Instead, they may be second-generation black holes, formed when two smaller black holes merge into a larger one. These mergers can create objects massive enough to cross theoretical boundaries. Another possibility involves the earliest stars in the universe. The first generation of stars, known as population 3 stars, formed from pristine hydrogen and helium shortly after the Big Bang. These stars may have grown far more massive than any stars we see today, collapsing in ways that modern stars cannot. But there is even a radical idea. Some physicists believe that certain black holes may not have formed from stars at all. Instead, they may be primordial black holes, objects created directly from extreme density fluctuations in the first moments after the Big Bang. If such black holes exist, they could explain why some black holes appear in places where no stars ever lived. They could even help explain dark matter, one of the greatest mysteries in cosmology. Yet black holes challenge physics in ways that go far beyond their origin. They also challenge our understanding of reality itself. According to general relativity, anything that crosses a black hole's event horizon is lost forever. Information is destroyed. But quantum mechanics tells us that information can never be destroyed. Both theories are extraordinarily successful. Both are supported by countless experiments. And yet, inside a black hole, they directly contradict each other. This contradiction is known as the black hole information paradox, and it remains one of the deepest unsolved problems in physics. Some theories suggest that information is encoded on the event horizon itself. Others propose that it slowly escapes through Hawking radiation. And some argue that space-time inside a black hole behaves in ways we do not yet understand. Whatever the answer is, black holes sit at the boundary between what we know and what we don't. That is why impossible black holes are so important. They are not abstract equations. They are not distant theories. They are real objects, shaping galaxies, warping space-time, and quietly exposing the limits of human knowledge. The black hole that should not exist does not announce itself. It emits no light. It makes no sound. It does not explode or collapse dramatically. It simply exists, silently orbiting its companion star, obeying gravity while defying theory. And sometimes, in science, that is enough. Throughout history, major breakthroughs have begun not with dramatic discoveries, but with small anomalies that refuse to disappear. Black holes were once dismissed as impossible. Now they are revealing that the universe is far stranger and far less predictable than we ever imagined. Somewhere in our galaxy, an impossible black hole continues its silent journey through space. It does not care about our equations. It does not care about our expectations. It exists. And as long as it exists, it reminds us of a humbling truth. The universe still holds secrets powerful enough to rewrite everything we think we know. If you want more real stories from deep space, subscribe to the channel and tell me